As I mentioned in previous lessons, there are three definitions of acids and bases. We have the Arrhenius, Bronsted-Lowry, and now the Lewis definition. So a little bit different. Be careful with these definitions here. I'll start off with an acid. A Lewis acid is any species that can accept an electron pair to make a bond. So it's an electron pair acceptor. Now be careful. Bronsted-Lowry definition, we also have acceptor and donor type definitions. In that one, it's an acceptor or donor of a proton. Here we have an acceptor of a pair of electrons. Now, in order for a substance to accept a pair of electrons, that substance must have an empty orbital in its valence shell. And I'll show you some examples of this. Conversely, a base is any substance that can donate an electron pair to make a bond. And again, we're talking about covalent bonds here. In order for a substance to be able to donate a pair of electrons, it must have a lone pair of electrons in its valence shell that it can donate and use to make a covalent bond. This type of bond where one atom gives both electrons is known as a coordinate covalent bond, sometimes known as a dative bond. Usually, each atom that is bonded to each other donates one electron. Those orbitals overlap, and then the two atoms share that pair. In this case, one atom, again, is given both electrons to be shared to make that covalent bond. So let's take a look at some examples, and there's some in your book. If you look on page 362 to 364, there are some examples. So what I'm going to do is I'm going to write an equation, and I'm going to show you with Lewis structures, and so you need to be able to do both. So I'll start with an equation. So we have ammonia and hydrogen ions reacting to make ammonia. So go ahead and let's draw the Lewis structures for both NH3 and H+. Go ahead and pause the video. So with our Lewis structures, what we want to show is the transfer of the electron pair from, in this case, nitrogen to the hydrogen ion. So we're going to show that with what's called a curly arrow. So that electron pair goes to hydrogen. That is used to make the covalent bond with hydrogen. And so we end up with something like that, where that's top hydrogen there in the Lewis structure. That's the one that's the new bond formed during this reaction. All right, let's take a look at another one. So a reaction between boron trichloride and nitrogen trichloride. This one might be easier to see after you draw a Lewis structure. So go ahead, pause the video, draw a Lewis structure for those two molecules kind of next to each other, and see if you can figure out what happens with the electron pair that is used to make the covalent bond. Pause the video. So going back to the definition, in order for a substance to be a Lewis acid, it needs to have an empty orbital that it can accept an electron pair. So the hybridization of boron in BCl3 is sp2, and it has an empty p orbital. And so that empty p orbital can be used to accept an electron pair. A base has to have a lone pair of electrons. And so here we see that in nitrogen trichloride, nitrogen has a lone pair of electrons. And let's show those being transferred to the boron. So how do we write this in our answer? So let me show you again. Look at the electron pair. It's going to be used to make a covalent bond between nitrogen and boron. So we can write it like this. I've seen it written that way before. Same thing up in the balanced equation, BCl3 plus NCl3, we can write that same thing there. So somehow show that there's a bond that forms between nitrogen and boron. Let's take a look at one more. So aluminum trichloride can react with more chloride ions to form Go ahead and draw Lewis structures for this whole thing. Go ahead and pause the video while you do that. Whole equation using Lewis structures. So here's what we end up with. We have aluminum again that has an empty orbital. Chloride has just electrons that it's not sharing with anybody. So one of those electron pairs can be used to make a covalent bond with aluminum. Notice how the hybridization of aluminum changes during this reaction. So it starts off as sp2. We have a trigonal planar molecule. And then in the ion AlCl4-, we end up with the hybridization of sp3. Just for time's sake, I left the lone pairs of electrons off of the chlorines, but you would definitely want to do that. So this theory is most useful for explaining acid-base reactions in non-aqueous solutions, and also for the formation of transition metal complexes. And we'll see some examples of those later on. All right, shifting gears to chapter 11, acid-base, more acid-base reactions. Let's talk about millimoles. We work primarily with moles and molarity, but there's something known as millimoles and even millimolarity. So a millimole is a thousandth of a mole. So sometimes it's better to express quantities in millimoles if it's really small rather than in moles. We'll see some examples of that. So we can use millimoles to determine the molarity of a solution, or we can use millimoles in the formula for molarity. So instead of moles over liters, we get millimoles, millimoles of solute, over milliliters of solution, and that'll give us molarity. Now take a look on 376 at example 11.2. This is a typical type of problem that we'll work on in this section, so read along with me. If 100 milliliters of 1 molar HCl and 100 milliliters of 0.8 molar NaOH solutions are mixed, what are the molarities of the solutes in the resulting solution? So first thing we need to do is find moles, or better yet, let's find millimoles of our reactants. So we have 1 millimole of HCl, I'm just looking at the solution here, and 1 millimole of NaOH that reacts, stoichiometrically at least. So that first one is, it says reaction ratio, and that would produce 1 millimole of NaCl and 1 millimole of water. I'm pretty sure that we have a limiting reactant here though. So if we look at how much we start off with, we have 100 millimoles of HCl, 80 millimoles of NaOH. So since they react in a 1-to-1 ratio, the NaOH is our limiting reactant. So we look at how much of the HCl reacts. 80 millimoles will react. 80 millimoles of NaOH reacts. You're left with 20 millimoles of HCl, our excess reactant, and 80 millimoles of NaCl produced. We can calculate concentrations by dividing by the, notice there, total volume. So millimoles divided by milliliters, total volume after those two solutions have been mixed, will give us the molarities of the substances in solution. All right, let's go ahead and try practice problem, or exercise rather, 14 on page 392. Go ahead and pause the video. All right, so let me show you a method kind of similar to what the book used. I call it the SCAR table. It's kind of like an ICE table, except we don't have an equilibrium system. S is how much you start with. So we have 1.38 moles of phosphoric acid, 4.28 moles of sodium hydroxide, and we have no water and no sodium phosphate. C is how much the amount changes by. So for reactants, the amounts are going to decrease. For products, the amounts are going to increase. And then AR after the reaction is complete. So again, this is not equilibrium, so it's not an E, it's after the reaction. So again, we have a limiting reactant situation. I believe the H3PO4s are limiting reactants. If you have 1.38 moles of phosphoric acid, you will need 3 times that amount of base to react with it, which would be 4.14. And so let's use those quantities. We have a 1-to-1 ratio of phosphoric acid to sodium phosphate. So however many moles of H3PO4 reacts is how many moles of Na3PO4 is produced. 3 times 1.3 is 4.14, so that's how many moles of NaOH reacts. Let's see how much we have after the reaction. Now, if we take those quantities and divide by the total volume, we have 250 milliliters of solution that we mix with 775 milliliters of solution for 1.025 liters. And that should get us our answers. Go ahead and pause the video and calculate those. So we should get about 0.14 because of the sig figs, 0.14 molar for the NaOH and 1.35, I believe, molar for the sodium phosphate. All right, take a look on page 377. Little different problem this time. This time we're looking for volume of 0.003 molar HCl. It's a pretty dilute solution. Probably want to use millimoles here. Would just neutralize 30 milliliters of 0.001 molar calcium hydroxide. So with all of these problems, make sure you write the balance equation for the reaction first. And so we see you need 2 moles of HCl, or 2 millimoles of HCl, for every 1 mole or millimole of calcium hydroxide. So we're going to take the volume and concentration of the base, use that to find millimoles. And then we'll apply our ratio to find out how many millimoles of HCl are needed for this reaction to occur. And then take our millimoles divided by the milliliters, which was, we're going to take the millimoles and divide it by the molarity of the HCl to find the volume of the HCl solution needed. So we can see that there in the solution. They'd set it up a little bit differently than I would. So again, I would find first separately millimoles of HCl needed for the reaction to occur. And that second step maybe, or just put that all over the molarity of the HCl solution. Millimoles over molarity equals milliliters. All right, got one for practice just like what we just looked at there. So go ahead and give this one a shot. It's number 24 on page 392. Again, make sure to write the balance equation first and then set it up. All right, pause the video. So here's our setup. So we take the volume of the barium hydroxide solution, multiply by its concentration. That'll give us millimoles, right? I'm using milliliters, millimoles. Barium hydroxide, I mislabeled in the conversion factor there. That should be millimoles. Two millimoles of acetic acid for every 1 millimole of barium hydroxide. That'll give us millimoles of acetic acid. Take that divided by its concentration, and that'll give us the volume. You'll need 31.3 milliliters of that solution. All right, pause and go to 378. All right, take a look at 11.4 at the top. It says if 100 milliliters of 1 molar sulfuric acid solution is mixed with 200 milliliters of 1 molar potassium hydroxide, what salt is produced and what is its molarity? So anytime you have this type of situation where you're given the quantities of both the acid and the base, set up a SCAR table. See if you have a limiting reactant situation or not, because you'll need to keep track of what the limiting reactant is. Maybe it's stoichiometric amounts, and either way, you'll be able to clearly see that in your setup. So we have, take a look, take the concentration of the solution, multiply by the volume. So we have 100 millimoles of H2SO4 and 200 millimoles of potassium hydroxide. They do react in a 1:2 ratio, so we do have stoichiometric amounts. And so that means you will produce 100 millimoles of potassium sulfate. Again, take that divided by the total volume, which is 300 milliliters. And you'll get your concentration, 0.333 molar for potassium sulfate. All right, back to 392. Go ahead and work on number 12. Pause the video. So as we see here, we do in fact have a limiting reactant. Our limiting reactant is the hydroiodic acid. And so we see that all of it reacts, only some of the barium hydroxide reacts. And so we need to know how much reacts so that we can figure out how much barium iodide is produced, 0.63 millimoles. Again, take that divided by the total volume, and you get our concentration, 0.023 molar for barium iodide. All right, that concludes this lesson. Let me know if you have any questions.